Were there scientists in the Middle Ages? Is there such a thing as medieval science? Well, the answer is complicated. But when Newton and Galileo were laying down their laws of motion in the 17th century, they were relying on work done hundreds of years before. In this video, I'll show you the medieval scholars who founded the science of mechanics and whose discoveries shaped later science. The first major developments in the medieval world were made by a man called Gerard of Brussels. We know basically nothing about Gerard's life, except that he lived between 1187 and 1260, presumably in Brussels. But a book he wrote survived. It's called Liber du Moto, or in English, the Book of Motion. In the book, Gerard was the first person to really define what speed is. He said that speed was the ratio of distance and time. It seems strange that no one before Gerard had worked this out, but there's a good reason why. Aristotle had studied motion, but all he could say was that some objects are faster or slower than each other. He never really got to grips with what speed actually is. Part of the reason was the Greeks were very reluctant to apply mathematics to the natural world. They especially didn't like working with things they called unlike quantities. To explain this, the Greeks were happy to say that one distance was double another distance. That is, you can divide distances by themselves without any bother. But they weren't happy to divide unlike quantities. So they were against the idea you could divide distance by time, because distance and time are two completely different things. Gerard made progress by just ignoring this rule. He said speed is simply distance divided by time, and that meant you could put an actual number on speed. From this point on, speed was a thing you could actually measure. It's easy to see why the idea that we can look at the world mathematically and measure it would have a profound effect on 17th century science. But there was an even more influential group of scholars called the Oxford Calculators. The Calculators were working at the University of Oxford in the 14th century. The most important were Richard Swineshead, William Heytesbury, and John Dumbleton. They took their name from a book by Swineshead, Liber Calculationum, or Book of Calculations. Their major discovery was that Gerard's definition of speed was only part of the story. Let's go back to our formula. If an object moves between A and B and its speed doesn't change, the formula works out fine. But the calculators asked a question. What happens if an object is speeding up or slowing down during a journey? In other words, what if it's accelerating? Well, clearly, the speed we calculate with the formula isn't always correct at every point, because the speed is changing. What the formula actually works out is the average speed. The calculators decided to study accelerating objects. They asked the question, what can we work out if the speed of an object is changing? Their great discovery was an idea called mean speed theorem. This isn't difficult exactly, but takes a little bit of getting your head around. Let's say you have an object that's accelerating at a constant rate. Well, the mean speed theorem can help you calculate its motion by comparing it with an object moving at a constant speed. Let's take an example. Imagine one object moving at a constant speed of 20 meters per second. Now imagine another object starting at 0 and speeding up evenly to 40 meters per second. The mean speed theorem says both objects will cover the same distance in the same time, because the accelerating object's average speed is also 20. One man who made this much easier to see was Nicolas Oresme, who was working in Paris in the 14th century. He came up with a way to turn the mean speed theorem into a picture. He drew something like an early graph, with time on one axis and speed on the other. On this graph, he first drew a line to represent the journey of an object moving at a constant speed. This is a horizontal line, as the speed isn't changing with time. He then drew another line for an object whose speed is increasing. Here, we have a line going straight up. Oresme realized something brilliant. The area under the line on the graph shows the distance travelled. He demonstrated that the area under the graph for the accelerating object was equal to the area under the graph for the object moving at a constant speed. Oresme's realization that the area under the graph is equal to the distance travelled is a clear precursor for Newton, and in fact, using graphs this way, putting two variables on perpendicular axes, was an original idea. Oresme did it almost 300 years before Descartes made it famous. Indeed, the influence of the calculators was profound, as one striking result shows. Let's say we have an object accelerating at a rate of 10 meters per second every second. We can draw a line on the graph to show how its speed increases. An important result, recognized by Oresme and the calculators, was that the object moves 3 times further in the second half of the time compared to the first. You can see this by comparing the area in the first half to the area in the second half. This result is interesting on its own, but it also has important historical significance. It's the same result found by Galileo when he was experimenting with objects falling under the influence of gravity. Of course, there are big differences between the calculators and Galileo. Galileo was testing and measuring his results in experiments, whereas the calculators were working on pure theory. Some people might say this disqualifies the calculators as real scientists, and this might be fair, but they were still working on scientific ideas, even if they weren't using the scientific method. There's a lot more I could say on the medieval study of motion. For example, I haven't even started today with John Buridan or Thomas Bradwardine, who both worked on improving Aristotle's theories, but that might be a topic for another day. If you'd like a video on that, or any other subject, please let me know in the comments. Until next time.